We're now going to discuss constrained problems. We've discussed unconstrained problems and derivatives. Today we'll talk about equality constraints, the next time inequality. We'll see that equality adds a little bit of difficulty, but not too bad. And inequality constraints definitely add more complications, at least from an algorithmic point of view. So let's jump into that. Just sharing my screen. There we go. I guess up front, just for this not to be confusing, KKT stands for the initials of three people, Karush, Kuhn, Tucker, three individuals who helped discover optimality conditions for constrained problems. When we say KKT conditions, we're usually referring to the full problem with equality and inequality constraints. So today we'll just talk about equality. So we usually don't think of that as it's a subset of the KKT conditions. All right, so just by way of reminder, this is the problem that we're trying to solve. We had chopped off these parts previously just to look at the unconstrained problem, but just reminding you of the notation we saw way back in chapter 1. These are inequality constraints. We're using G for inequality constraints, H for equality constraints, and in general, there may be many inequality and equality constraints. And then we have bound constraints. And of course, we could treat bound constraints as inequality constraints, but it's much more efficient to, if they are actual bounds, to signify them as bounds. Here's just an example of a 2D problem, so we could visualize it. The blue would be our objective contours, and if it was unconstrained, we jump all the way over to the minimum point. But now we have these constraints, so we've got this sort of round elliptical constraint here that says we have to be on the outside of that. So these are both inequality constraints. So we have to be on we can't be on the outside. That's what this red means. These are regions we can't be in. And then this quadratic constraint here where we're constrained from being on the outside of that one. So this white area is the feasible. And within that feasible region, this is the minimum within the feasible region. So that's our constrained optimal solution. In this case, note that both constraints are what we would call active. That means we are right up at the boundary. So both of these, we would usually say, right, like G1 of X has to be less than or equal to 0. G2 of X is less than or equal to 0. In both cases, they're equal, right? That's what we call active. They're right up at the line. If, for example, we made this ellipse bigger, let's just say we ignored that ellipse there and it was like way out here, right? Then we'd probably end up more over here. The minimum is probably a bit more over here now, but we're not up at the edge of this one. So that would be an inactive constraint. Again, this is just by way of review here. Okay, so let's try to derive our optimality. Actually, before we do any derivation, let's just think about a motivating problem. We will have done or will be doing this in class in more detail, but if you're not there, this is just worth thinking about before we get into the math. So we won't do it as much detail as we do in class. You might want to pause and try on your own to think about it more, but let's just consider a very simple problem. Just so we can visualize really easy, we'll do it in 2D and we'll have just this linear constraint. Okay, so we want to minimize that. Subject to, we'll put a circle. Circle is probably the easiest thing to do. Okay, so just one constraint and just a 2D problem. Okay, so here's some questions you might ask yourself. First, what's the unconstrained optimum? It's straightforward to figure out. And then draw the gradient vectors. So the gradient is the gradient of the objective. Draw some vectors. And then also draw the gradient for this constraint. There's just one constraint, so it's a gradient, not Jacobian. But so one constraint. Draw the gradient vector in a bunch of different places. Okay. And then think about where the optimal solution is and what the relationship between those gradient vectors are. And think about why that's the case. Why is this the optimum? And maybe think about how you might define that mathematically. Okay, so this will take a little bit of thought. And like I said, if you haven't done this, you may want to pause and do that. I'm gonna do it really quickly here for you. Let's just draw this. So here's x1, here's x2. My objective contours are going to look like this. There's going to be lines where x1 plus x2 is constant. So, I mean, you could see right away, what's the minimum of this if there is no constraints? It's going to be minus infinity, right? We want to go way down to the bottom left. So our objective contours are just going to be these lines. These are going to be values of constant x1 plus x2. So the gradient is going to be always in the direction of steepest increase. So it's going to be in that direction. It doesn't matter where I am, right? It's constant in this case, and that's just only because I have a linear objective. As we've seen in general, the gradient is going to change as we move around, but in this case, I just have a linear objective, so the gradient is constant. Derivatives of a linear thing is constant. Okay, my constraint is a circle. So I've got this circle. And since I'm doing an equality constraint, that means I have to lie on this circle. Okay, I'm free to pick any solution, but it has to be on this circle. So we can see right away that the minimum is going to be right here, right? That's the furthest to the bottom left I can go while still staying on that circle. But if we were to write our constraint in our usual form, right, we would say we like to set it equal to 0, right, by convention. Okay, and so then the derivative of this function, the derivative of h, is going to be the partial of h with respect to x1, comma, the partial of h with respect to x2, right? It's a vector. So in this case, it's 2x1, 2x2. All right, so if I'm over here on this upper right quadrant, that's going to be a positive vector. It's going to point like this. That's the gradient of h. If I'm over here, x1 is negative, x2 is positive. That's going to point like this. And as you can start to see, actually what's going to happen is no matter where I pick, it's always going to point perpendicular to this circle, right? So here at the optimum, it's going to point like this. Okay, so you may have noticed that what's happening at the optimum is that these two vectors are parallel to each other. And that may make some intuitive sense. So it's hard to think about this in general, but with this simple example, you could imagine this. Imagine this was a wire, okay? And I put a bead around the wire. So the bead is free to slide around the wire, but it's stuck to the wire because it's a constraint, right? It can move wherever it wants as long as it stays on the wire. And now I want to minimize my objective. So it's like, let's say I've got this bead here. Right, here's my bead. It's attached to this wire. Let me draw a different color. And I'm going to put a string. I'm going to pull that string in the direction of decrease because I'm trying to decrease this as much as possible. And you can see that it's going to slide because there's a component of that force, right? There's a component of the force that's in the direction that I can still move. So it's going to slide until it gets all the way to here. Once it gets to the bottom, right, my gradient vector says, okay, here's a descent direction this way. My descent directions are going down to the left, but that's parallel to the gradient of my constraint, which says the gradient of the constraint is pointing in directions that I can move perpendicular to. So now that these are parallel, there's nowhere for me to go. I can't descend any further. So what we've said is that, at least from this simple example, it seems like we want the gradient of f to be parallel to the gradient of h. Mathematically, we could write it like this, that the gradient of f equals is not equal to gradient of h, but is multiplied by some scalar. Okay, since they're in the same direction, I know that there's some scalar. I don't know what the magnitude of this scalar lambda is, but there's some scalar that if I multiplied them together, I'd make them equal. And maybe lambda is positive, maybe it's negative. I don't really know yet. And by convention, we're actually going to put a negative sign here. That didn't really change anything, right? It's true what we said. We could have defined lambda to be positive or negative, but that'll actually be more consistent. That'll be consistent with what we're going to do with inequality constraints and our convention. So our convention for inequality, I should say. So we're going to put a negative sign. So let's just go with that for now. Okay, so this is not a proof. We're just kind of motivating an idea here. All right, so let's do this a little bit more formally. Let's look at optimality conditions. And first, we're going to do a bit of review. Let's think about it as if it was unconstrained. So let's say I've got some point here, right? And I've got some objective function and constraints, and I'm looking for directions p that I can move in. Okay, and so we're going to take a Taylor series above our objective, just like we did before. Could say, well, this is going to be f of x, and p is some small step that I want to take. So it's going to be the gradient of f times p. Okay, is a dot product. And there are second order terms, but if p is a small enough step, then this is a good approximation. So this is my first order approximation. Now, if let's say I was at a minimum, let's say this point here, x star is my minimum, right? In other words, this is a minimum. So any step, if that was true, right? If this was really true, then any step I take would have to take me to a point that's bigger, right? If x star was truly a minimum, then no matter which direction I go, p could be anywhere I go, it's got to be greater than or equal to the point I'm currently at. That means I'm at a minimum, right? Okay, so if that's true, if we look at this equation above, right, and let's say I could move this over to this side, I move this over, it says this term, let me just do it. This also says that x star plus p minus f of x star has to be greater than or equal to 0, right? So if I take this term and move it over, that's the same as this. So it's saying that this term here must be greater than or equal to 0. So we're saying that this is a minimum if that's true. And that should also make sense just from the definition of a directional derivative. This is saying that any direction I go is positive or greater than, or at least it's non-negative, right? It means that any direction I go, the function would increase. But as we talked about before with unconstrained problems, that's impossible unless the gradient of f is 0, right? So here it is in a picture. Let's say here's some function, here's the gradient of f. We know that if we go on this half plane, anything that's on this opposite half direction, right? If I take a line perpendicular to the gradient of f, everything over here is a descent direction. That's, remember, we saw this from a directional derivative. So any direction I pick over here is a descent direction. So that means I can always keep going down. I can always find a descent direction unless the gradient of f is equal to 0. Once I find a point where the gradient of f is 0, then I'm at a minimum. Okay, and so that's what we saw with unconstrained optimization. This was maybe just a bit of a review here. But now let's build on that. Okay, let's build on that and let's consider constraints. So now let's say I've got this constraint and I've got maybe a bunch of constraints. And my constraints, same thing, I'm going to be at some point and I want to consider what type of steps I can take. And so I've got j constraints and I'm at some point x and I'm considering possible directions that I can go from here. And again, we'll do the same thing. We'll do a first order Taylor series here. So this is going to give me my constraint plus the gradient of my constraint dotted into that step. And again, plus higher order terms, which again, for small steps, we can consider to be small neglect. All right, so for this point, let's say x is x star, for this point x to be an optimum, what do we require of h? Well, remember, if this is truly an optimum, right, then h better be 0, because that's what it means for me to satisfy my constraint problem. I'm trying to find the minimum subject to my constraints, and the constraints are, in this case, equality constraints, so h is 0. So if I'm already at a point that h is 0 and I want to go to a new point, this new point here, I could only take steps for which that's also true. If I take a step and h is still 0, then that's fine. That's a feasible direction. I'm perfectly able to move there. That's a valid step. So if that's 0 and that's 0, what we're saying then is that for this to be a feasible, so we're not talking about descent direction here, we're talking about a feasible direction, then I need a gradient of h transposed into p to be equal to 0. Okay, so this says that a feasible direction is one that's perpendicular to all of my equality constraints. Okay, And that's kind of like what we saw here, right? That here's my equality constraint, and a direction that was feasible was perpendicular to that. So the equality constraint always points out from that circle. It's always pointing away from that circle. So I can always move perpendicular to that. In other words, I can move always in this circle. So that's what this is telling us. All right, so here's a picture of that. So here's, for example, one constraint. So here is some plane I can move. That's perpendicular. So imagine this point is sticking out, and I consider this plane that's perpendicular to that vector. So if this is the gradient of my constraint, I'm free to move in this plane, at least the first order, right? All of this never works if I go too far away, because remember, we took a first order Taylor series. We're ignoring big terms, but we're saying for small steps, I can go perpendicular to that vector here. So this plane defines my feasible steps. Now imagine I've got two constraints here, right? So there's a vector, these two vectors, black and red. So now this one plane is perpendicular to this one, and I've got a different vector pointing another way. And so it makes another plane perpendicular to that one. The intersection of these two planes defines a line. So it says this blue, this line is all I can move in. So as I add more equality constraints, as you'd expect, this is like adding more equations, right? These are equations, like this is almost like a solver here, equations, except for we have also an objective. But if I just had equality constraints, I'm adding more conditions to my problem. So I'm decreasing the space that I can move in, at least for these equality constraints. Okay, so let's now put these things together. We said that for a descent direction, well, to be a minimum, we required that this was true, that any step would have to increase, okay? Any step but now we're adding the condition that the only P's that we can take that are gonna be feasible are ones that also satisfy this condition. Okay, so we have a second condition. We need P's that are gonna make us remain feasible. That's when we derived. And of those feasible P's, then all of them better increase the function. And if that's the case, then we are at a constrained minimum. It means that our constraint is still satisfied, and any other direction that we could go that still satisfied the constraints would have increased our function. So this is a constrained minimum. Okay. This may not be obvious, but I'm not going to prove it here. But the only way that this can be satisfied, both of these conditions can be satisfied simultaneously, is if the gradient of the function is, let's just do one constraint first, is parallel to the gradient of the constraint, okay? But to generalize this, we're generally going to have more than one constraint. So I need to think about multiple constraints. So I'm going to have multiple lambdas. Oops, lambda j. Sorry, I keep messing up here. Lambda j, and then I'm going to sum over j to the number of constraints I have. Sorry. And again, we're going to put a negative sign. Again, that's not necessary per se for equality constraints, but it's consistent with what we're going to do with inequality constraints. It doesn't really matter in this case. Okay, so if that's the case, another way we could write this is this. We could move everything to the right. We could say the gradient of f plus the sum of lambda times the gradient of h equals 0. Okay. So what we're saying here, these are the conditions we derived, and what we can prove, although I didn't prove it, like I said, is that there's always a solution. You can always find a step that will satisfy this constraint and will and could lead to a decrease unless this condition here is true. Okay, unless the gradient of f is perpendicular to this linear combination of my constraint gradients. Okay, so this is actually really convenient the way we've written this here at the bottom. So what we're going to do is we're going to define this function L, give it a script L, and we call this the Lagrangian. Okay, so if I define the Lagrangian, this is the Lagrangian. it is equal to f of x, plus the sum of lambda times h of x, okay? And notice this condition here is equivalent to saying the gradient of lambda. Actually, let me just be explicit. Well, yeah, I'll just write it that way. The gradient of the Lagrangian with respect to x is equal to 0. So this becomes our new first order optimality condition. It's not true anymore that the gradient of f is 0. Right, that worked for an unconstrained problem, but that's not true anymore for an unconstrained problem. What we need is that the gradient of the Lagrangian is 0, okay? So this function here we call the Lagrangian, and these terms lambda we call Lagrange multipliers. Let me just write that too. Lambda is called a Lagrange multiplier. Okay. Now we said that the gradient of f is not 0, right? That's certainly clear from this problem, for example. Here the gradient of f is nowhere 0, right? I mean, it's not 0 anywhere, but we still have a constrained optimum. It's the point here where the gradient of the Lagrangian is 0, which happens to be right here. Okay. I'm going to revisit this Lagrangian, but just want to also sort of try to help with this intuition that the gradient of f and the gradient of h should be parallel. We saw this already, but here's another way to maybe visualize this in a more three-dimensional space here. Let's first consider this figure on the right. The gradient of f, right, that's my steepest increase. So everything on the half plane, so if I draw a plane perpendicular to that, everything in this half plane below, these are all descent directions. So any one of those would decrease my objective. So if I can go to anywhere in that blue, that's great. I'm decreasing my objective. Now h, remember my gradient vector for h, for an individual h here, we saw at first order that I could move perpendicular to that vector. That means that my constraint is not changing, right? Because the gradient of h dotted into a step is 0. So my directional derivative is 0. In other words, my constraint's not 0. I'm staying feasible. If these two vectors are not aligned, then you could see this plane would dip down into this blue area. So there's a direction here, there's a region here where I'm still staying on the red, I'm still staying feasible, but I'm also descending. And again, I can't go too far, right? Because we did this first order, but at least there's still some small steps here where I'm staying feasible and I'm descending. So I can't be at a minimum. The only way this could be at a minimum is if these two vectors were aligned. If that's the case, then anywhere I move here doesn't change my constraint, but it also isn't changing my objective, so I'm not able to descend any further. Okay, so let's get back to that Lagrangian. Just kind of recap here again. This is what we call the Lagrangian. It's the objective. I'm going to write it another way. I'm just writing it here as a dot product, or we could write it explicitly as a sum, right? It's the same thing. Lambda j times hj, whichever way you're more comfortable with. This is what we define as the Lagrangian. One way you could think about what we've done here is we've taken a constrained problem and we've turned it now into an unconstrained problem with more variables. We added these new variables, lambda, which we don't know what they are beforehand, right? They're additional unknowns, just like x. We don't know what they are, so we actually have to solve them together. So if we thought about it in that way, let's think about this as our new unconstrained function with more variables. And so if it was an unconstrained problem, we need the gradient of Lagrangian to be 0, just like we need the gradient of f to be 0. Same for an unconstrained problem. The only difference here is that I have more variables. So I need the gradient with respect to x to be 0, and in the gradient, that's a lambda. I need the gradient with respect to lambda to be 0. Right, I need all my derivatives to be 0. So let's just write that out. I need the partials of the Lagrangian with respect to each x to be 0. And let's just do that. That means that I need the partial of f with respect to xi plus the sum. This is a sum. I'm going to use the sum j. Lambda is a constant because we're just doing a partial derivative. And I get the partial of hj with respect to xi equals 0. Okay, and that's the condition that we derived. Well, we didn't derive, that we stated here based on this part of the derivation. So that looks good. Let's take the partial of our Lagrangian with respect to lambda. That needs to be 0. So the derivative with respect to lambda j is just going to be hj because those are just multiplied together. So that just says hj equals 0 for each j, which is what we want. In other words, we're saying our constraints must be satisfied. So indeed, this formulation gives us what we want. It satisfies our first order optimality condition, and it satisfies all our constraints. So this is at least the equality constrained version of what we call the KKT conditions. Now, just like the unconstrained problem, you'll remember that while there's a first order condition, there's also a second order, and that's true here. And the second order is very similar. It's that we, remember for unconstrained, we needed the Hessian to be positive definite. In this case, we need the Hessian of the Lagrangian. In other words, the second derivatives of the Lagrangian. We need this vector with respect to x. That needs to be positive definite for all feasible steps. We won't generally worry about that explicitly, just like we didn't for the unconstrained case, because we will take descent directions, but just want to state that for completeness. Okay, let's just do one quick example here. Just a simple, small problem. So let's say I've got, it's very similar to the one we did with the plane. Let's just change the numbers a little bit though. So here's a linear objective, and I'm gonna have a different constraint, but fairly similar. So subject to 1/4 x1 squared plus x2 squared minus 1 equals 0. And this is an example from our book. All right, so let's solve it the way that we suggested here. This isn't the way we're going to necessarily do this always, but where we're going to form this Lagrangian and just take partial derivatives. We'll treat it like it's an unconstrained problem. So now I've got this Lagrangian. It's a function of x1, x2, and I have to have one lambda for each constraint. In this case, there's only one constraint, so I just have one lambda. So now I'm forming this new unconstrained problem. So it's f plus lambda times h. 1/4 x1 squared plus x2 squared minus 1. Now I just take, we're going to do what we did from calculus. Again, this is not what we're going to do with optimization per se, but this will be a good way to kind of motivate to the calculus procedure here. Just take partial derivatives and set it equal to 0. You take the partial with respect to x1. That gives me 1 plus 1/2 lambda x1. We set that equal to 0. I do the partial with respect to x2. I'm going to do the partial with respect to lambda. Okay, and so when I do that, I'm going to get 3 equations and 3 unknowns. I'm not going to write it all out here, but it's just math from here. Boy, I didn't write that well. Sometimes confusing my lambdas and my h's. That is a lambda times x1. Okay, so there are 3 equations, there are 3 unknowns. They're not linear equations. They're actually, a little bit more of a pain to solve. There's some quadratic terms. I've got things that are being multiplied together, but I could solve this. And what's going to happen is I'm going to get 2 solutions, okay? I'm just going to show you that graphically. There are 2 solutions. As you'd expect, one is a min and one is a max here. So there's a min and a max because I'm only applying the first order condition here. I'm not actually doing a descent method here. This is just the calculus version. So I can't distinguish between critical points without looking at the second order condition. But what you notice is that, as we expect, the gradient of f and the gradient of h are perpendicular at these points. Not perpendicular, sorry, parallel. And if we were to look at the minimum, right, if we were to actually look at this Lagrangian, once we solve it, we're going to get an answer for x1 equals some number, x2 equals some number, lambda equals some number. So if I took that lambda that I now know, just for fun here, plug it back up here, and I want to plot that. I just want to visualize what that Lagrangian looks like. And this is what it looks like. So it's kind of like the same objective we were doing before, right? Whereas this linear thing, we had this ellipse kind of problem. and here is the constrained optimum. This black is what that Lagrangian looks like. So you can see it's like this unconstrained problem where the minimum of that unconstrained problem corresponds to the solution to my constrained problem. And that's just interesting. It's a visual. Unfortunately, we can't really do that because to make this plot, I had to know what lambda was, but I don't know what lambda is before, and that's something I actually have to solve for. That was a new unknown, but this is just to kind of show you intuitively that this idea that this is actually going to give me the correct solution. Okay, so what we're going to go from here next time is we're going to deal with inequality constraints. And see how that changes things. And eventually we're going to try and figure out how we actually solve this in an algorithmic procedure where we're going to do descents. Because as we saw here, this type of procedure potentially is going to lead to this big system of equations that may be hard to solve. It's still fairly doable for equality constraints, but as we'll see, it gets more complicated for inequality. And so we're going to have a different procedure than just take partial derivatives and set them all equal 0 and solve a big set of nonlinear coupled equations. All right, so next time we'll get into inequality constraints.